A few years back, I was working at a startup that had an enormous product catalog that was constantly updated and people needed to search through it. And I got into a debate with a colleague of mine because the data was in MySQL and he wanted to start regularly exporting it out and shipping it across into Elasticsearch because he thought the search capabilities would be better. And I thought, that's a great idea in theory, but making that run efficiently and reliably every day was just going to be an ongoing maintenance problem that our startup didn't need. We debated it back and forth, and in the end we went ahead, and it turns out we were both right. It was painful to set up, it was never quite fast enough to be up to date, and it was reliable except on days when it wasn't, and those days just took all productivity out of the window. But it was worth it. It was a much better experience. It was painful, but it was worth it. Could it have been less painful? When you need, as so often you do, to pull data from these places, do something with it and stick it into those places, is there a good generalized solution to that problem? And that's today's topic. We're going to look at Apache Flink, which has been getting a lot of interest in this space, and it's designed to solve exactly that kind of problem. So I've pulled in Robert Metzger, who's on the PMC for Flink, and I'm going to get him to explain what Flink does and how it does it. And in this conversation, we managed to go all the way from why does Flink exist and how did he get involved, to how sophisticated can you make the data processing part? What options do you have? What languages can you use? And how do you recover when the process crashes? What's its crash recovery and scalability story? And lots more. So let's talk about Flink. Let's ship some data around. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Robert Metzger. Robert Metzger, thanks for joining us. How are you doing?
Good, thank you. I'm really excited to be here on the podcast to talk about Flink today.
Yeah, I'm very excited to learn more about Flink because there's a lot of buzz about it, but I've never really sat down with an expert and really understood what's going on. So you can fill me in from scratch.
Yeah, let's do it.
Okay. So let's start with your credentials. Why are you a Flink expert? How did you get into it and what do you do with it?
I try to keep the story as short as possible. So when I was studying in the Technical University in Berlin in like 2012, 13 or so, I was working with a bunch of PhD students there that were building a big data system called Stratosphere that was about competing with Apache Hadoop. Basically, they had like a database background and thought that there's so many findings in like 30 years of database research that have not really been considered with Apache Hadoop. And they wanted to take these learnings and add them to a big data system. And then a few events happened. So we open sourced this research project, donated it to the Apache Software Foundation. We started fundraising. I became a co-founder of a company called Data Artisans. Now it's called Ververica, that set out to commercialize Apache Flink as a technology. Back when we started the company, we still intended to build a batch processing framework, but it was actually an outside contribution to add a stream processing API on top of the engine. Because the engine, as I mentioned, is based on database principles, and databases use this concept called pipeline execution, where multiple operators are running at the same time. And this sounds very much like stream processing, right? Like operators running all the time processing data. So it was actually quite easy to add an API on top of this engine for stream processing primitives. And of course, then we added a lot more things to the engine, like checkpointing, event time and watermark support, the state backends, and so on and so forth, to make it a, let's say, real stream processor. And so going back to this contribution, was that we noticed that there was a lot more interest in our stream processing capabilities compared to the batch processing capabilities that Flink was offering. And also to some extent, I mean, Apache Spark was rising very quickly at that time as an alternative to Hadoop. And I think they were, let's say, winning the race in the batch processing space.
Okay.
And this is how I learned Flink and all of that, because I was basically working as a student on the stuff and started a company around it. I helped building the open source community as part of Apache. And we did a successful exit of the company to Alibaba. They are offering Flink in their cloud product. And like 1.5 years ago, I switched to Decodable to work on making Flink more accessible as part of a stream processing platform, basically, which is also based on Flink.
So your entire career has been in Flink?
Yes.
Are you happy with that?
Yeah, but of course, like after, I don't know, 10 years or so almost in the same technology, you start to wonder if you also need to look left and right. But of course, I mean, Flink is a really big project, not as big as like the Linux kernel, but there are like subsystems in Flink, completely different APIs and abstractions, and you can go very deep in many areas. So there's a lot of very different areas in Flink to work on very different problems.
Yeah, any large enough project becomes a whole sub-world, right? A little universe in itself. Yeah. Okay, so you've raised a lot of things we need to get into, but before we get there, just for context, give me a typical example of how someone uses Flink to solve some problem.
So let's say you have some relational database like MySQL, and you're noticing that your full text search queries are taking too much time on that database. So you want to offload these types of queries from your transactional database into something that is more purpose-built, something like Elasticsearch. Yeah. So you would use Debezium for change data capture to follow the changes on this transactional database, then perform some joins in Flink to combine data from different tables into, let's say, one big document. And then you ingest these documents into Elasticsearch. So basically, you're not using Debezium as a standalone system. You could do that and use like Kafka in between. But in this case, Debezium would run as part of a Flink connector. So there is connectors in Flink that are based on Debezium that allow you to follow changes on a transactional database. And then you can use, for example, Flink SQL to express this join of multiple tables and filtering, whatever, aggregations. And then you use a Elasticsearch sink in Flink to write this data to Elasticsearch. And in effect, you have something like a continuous real-time join from multiple different tables. And whenever there's an update, you basically instantly get an update in Elasticsearch to always have your data fresh and up to date.
Okay, so the main thing it's doing for you is, in combination with Debezium, slurping that data out from one place, a certain amount of processing to transform it as you load it into another place.
I think the core of Flink is the processing. The core really is how Flink is able to do this real-time join in this particular example. There's many other examples. You can also do machine learning stuff with it. You can do aggregations. But that's the core, what Flink is mostly about, like real-time stream processing. The connectors are more a necessity to get your data in and out of Flink.
Yeah, it's not going to do much without those.
Yeah.
But the essence of the project is...
there are other stream processors like Kafka Streams, for example, which are only working with Kafka as a data source. But Flink is independent of data sources.
Okay. How many data sources and sinks does it support? Roughly.
So I think the core project has maybe like 8-ish. And then there's probably like 20 or 30 that are in other repositories or somehow available publicly.
Okay.
But all the important stuff is covered, like Pulsar, Kinesis, Kafka. On the sync side, you can do any JDBC database. You can do writing to S3. You can I mean, any file system, actually. You can monitor for changes. You can write to these file systems in various bucketing, like time-based bucketing, database bucketing, whatever. So there's a ton of options for getting your data in and out. And to be honest, if there is a rare case where you have like a custom system, then it's also not terribly hard to build your own source or sink in Flink.
Okay. Does it ever get used for like, is it always transforming the data and sending it to other places, or does it ever get used just for straight reporting?
I mean, you can use Flink. So what do you mean by reporting?
Like, I guess what I mean is, could you have like a CSV or a PDF as your sink?
CSV for sure. That's supported out of the box. So you can write like CSV or more popular like Parquet files, for example, or you can write in the iceberg formats to S3 or something. So you can definitely use Flink also for getting your data in the shape that you want, like for loading your data warehouse, for example.
Okay. I only asked that because I'm always thinking like, what's the smallest possible change I could make to introduce this to a project? Yeah. Okay. In that case, I think we should dig down into how it actually works. What do I need to understand about Flink's architecture?
So Flink has a few basic building blocks that you use to express your workload. So the core is a data flow graph, like a set of operators, let's say a Kafka source and a CDC source, and then a bunch of operators like transformations, filters, aggregations, joins, and they can be arbitrarily complex. Like, trust me, they can fill entire screens if you visualize them with like hundreds of operators, really. I mean, okay, hundreds is maybe an extreme case, but like 30, 40 operators is really not unheard of.
Okay.
And you basically use one of the APIs in Flink, like the Java or Scala API, or the SQL API, or the Python API, to build this data flow graph. So basically to define the structure of your Flink job and to define either the logic of predefined operators. So Flink has, for example, windowing operators that allow you to window data into hourly buckets or something.
Right.
Or session windows where you want to analyze, like, have basically dynamic windows that are just have the size of a certain user activity. And so you define the structure, and then you also define the logic of what is happening inside these operators. And then the engine knows how to execute this graph efficiently on a cluster of machines. So if your workload is increasing, you can change the number of instances, the parallelism of your job in Flink, and then you will execute this on more machines.
Okay. I'm just trying to think how that's going to look. So what do I do if I'm using SQL? Am I doing something like create thing that looks like table but is actually a slurping from my SQL?
Pretty much, yes. So
And then I can join to that in my from clause later.
Exactly. So basically, you're defining a stream as like a table in Flink SQL. So when you want to read from a number of Kafka brokers or whatever, like Kafka clusters, you do a create table statement for each of these data sources. So Flink SQL supports all the data, all the connectors that I've mentioned. So you can create, they do like whatever. If you have a Kafka topic called users, you do basically create table users, and then you define the fields in your Kafka topic. And let's say the data is in JSON, so you define like a JSON deserializer, and then Flink knows how to read the JSON data from your Kafka topic to analyze it. So you do like a create table to expose your Kafka topic in Flink SQL. And then if you want to do, for example, a filter, you just do select star from this table. And then in the where clause, you can define your filter. or you
And,
select, or you read from multiple tables and you do a join.
right. So I'm going to make you flinch again because I'm going to mention CSV again. Do I also do like create table as output.csv and then insert into output table select star from?
Exactly. Yes.
It just looks like regular SQL type
Yes.
operations.
Yes.
But there's no underlying storage. The underlying storage is just outside of Flink.
Exactly. Flink doesn't come with any storage. So
Okay.
you define S3 as a storage or local file system or whatever. Yeah.
Okay, so the next question that raises, you say it will automatically distribute the jobs across nodes. How is that working?
So there's a central so when you're building this data flow representation in your, let's say, Java API or in SQL, you're typically doing this on some kind of client instance. So either it's the SQL shell that you're using, or it's a Java application that you're implementing, and the Java application knows how to connect to what is called the job manager process of Flink. So the job manager is the central component that is coordinating the execution of a Flink job, or actually also multiple Flink jobs. So Flink supports both single or multiple jobs on a job manager. And the job manager is creating a distributed representation of this data flow graph, and is basically splitting out. So if you have like Kafka sources, some join operator, and a CSV sink, then it will create multiple instances of these operators. Like if you're running this on 10 machines, then it will create 10 Kafka sources, 10 join operators, and 10 CSV sinks. And the work will then get distributed from the job manager to the so-called task managers. So task managers are the workers that are running on all the cluster nodes. And as you add or remove task managers, you can scale up or scale down the resources that are available for processing.
And can you do that dynamically? Can you just throw more machines at it?
Yeah, that's a feature that we've added in Flink. I don't know, like 1.13 or 14, I don't know, maybe earlier. So it is a feature that has been added to Flink, let's say recently.
For a given value
like
of recent.
2 years ago or so.
Okay.
That allows you, it's called the reactive mode in Flink, and it basically allows you to add or remove machines, and Flink will dynamically grow and shrink.
Okay.
And that's pretty neat if you're using something like Kubernetes horizontal pod autoscalers. So Kubernetes will monitor like CPU usage, and if it goes too high, it will just add more machines. You can do the same with like EC2 autoscaling groups or something.
Okay, that makes sense. And is there, I'm just trying to figure out this SQL interface. Is there something like the notion of a temporary table? Can I join two things, stick them into one logical table while I think about how I want to select that data out?
So you don't have to worry too much about the representation, like how Flink is representing a table or a join in your SQL statement. So Flink will, of course, internally. So it really depends on what you're doing. So if you do let's go back to the example that we had earlier, some user table, and you do like a select star, and let's say you're reading from Kafka, you're filtering, and you're writing to Kafka. Then it's really, data is just flowing through the system. It's never materialized in the system. It's just passing through, and we are filtering out some, like if you do like a insert into target, select star from users where X smaller 10 or whatever, then it will filter out all the elements based on that predicate.
Okay.
But of course, if you do something like a join and your input So let's say you have this user table and you want to enrich some information in this user table from a database table. So you have this stream of user data, and you have a MySQL database that contains, let's say, the address of each user. And you could do something like a database query for every user, like a query on MySQL for every user that comes. But of course, you would bombard your MySQL server with queries for every incoming record in the stream processor. Your stream processor would actually be slowed down to the speed of your MySQL server. And that's not what you want for a massively parallel system like Flink.
Yeah.
So what you do instead is that you do change data capture on this MySQL table. So you do an initial snapshot of all the data in the MySQL table, load it into Flink state, and then you subscribe to further updates from that table. So whenever like a user address is changing, we are updating this data in Flink state, and Flink can then do the lookup locally in its state backend. Okay. So you don't have to do any network access for this particular state lookup. It will just be in the local RocksDB instance of the task manager.
Okay, yeah.
So that's a lookup join in Flink SQL, and that's where Flink SQL will decide that one side of the join, the side with the address information from MySQL, needs to be stored in Flink state, but the user data that is flowing will not be persisted. But there are cases where you're joining two tables and you're materializing both sides of the join. And whenever any of the two inputs are updating, you produce an output result, like an output event that will send downstream, and then the sink has to decide what to do with it.
Okay, that leads naturally to two questions. One's about time and windowing, but first, you're saying that, like for the address thing, you're maintaining what is essentially a local read-only replica of MySQL's address table,
yes.
Right?
Yeah.
How is that state management working in Flink? Because you said Flink doesn't do any storage. So what's going on?
It is, okay, I was lying to you. Let's just say it was for the sake of making it easy to understand.
We can separate between logical and physical storage, sure.
So Flink, the project itself, doesn't provide any permanent storage like a MySQL server to persist your data in your database tables. But Flink needs a lot of temporary storage, and that's what we generally call state. So state can be as small and simple as the current Kafka offset that you're reading from, and it can be as big as your entire address table from MySQL. So we have customers that are using Flink with like 250 gigs of state in their joins, and even that is small. Like if you talk to Apple or Netflix, which are using Flink in production, they're really talking about terabytes of state that they're maintaining across their task managers.
Okay,
and so a lot of things that we've implemented in Flink are about the state management, because I think that's also why I think we say on the website Flink is doing stateful stream processing. So this ability to maintain state inside the operators is what makes Flink really interesting. Because if you just without state, Flink would just be a system that allows you to move data from left to right, but it cannot really maintain or build up any knowledge about the outside world. So with Flink, you can basically, you have like memory. You know what happened before, and you can make some decisions based on what happened before. Like in the case of this lookup join, you know what is in the MySQL table, and you know that Flink is always making sure that you're not losing any data. So even if you kill one of those task managers or multiple of these task managers, Flink is able to recover this state and restore it for you, and you will never notice that there was any loss of state temporarily because the task manager has died.
Okay, this presumably is also the same mechanism you use to calculate aggregates that are live updating, right?
Exactly. So you can store aggregates in state. Yes.
Yeah. We should probably talk a little bit about the difference here between static data and live data, because you say Flink was originally built for like batch files. But you can, just to give it a really simple example, I can say something like count star of users, and I would expect that count to be gradually rising as people register on my site.
Yeah.
So you have. So what's Flink's notion of a live stream of data if everything's a create table statement? Or is all data in, even the stuff that looks static, is all data in Flink considered just a stream of data coming in?
From an engine perspective, yes. So even if you're reading, like if you're doing a classical batch use case, you have, I don't know, a few terabytes of data in your S3, and you want to join it and filter some data and then write it to Snowflake. And this is a batch job. This is a finite batch job. You're starting, and Flink will execute this in a streaming fashion. So it will just start reading the files in S3, stream them through the join operators and whatever other operators you have, and then load them into Snowflake. And once it's done reading the files, it will shut down and the job will be done.
Okay.
This is
so
also
it's kind of treating batch as a special case of streaming.
correct. Yes.
Yeah. Okay. That keeps things. Well, I'm assuming that keeps things simpler, but we should go deeper into how it processes, like joins. How do you do streaming joins? What's Flink's notion of that?
If you know that you're processing a finite stream, you can do more optimizations than when you're processing an infinite stream. So if you're doing batch processing, you have a finite stream. So you know that you can write all your data on disk. You will be able to, assuming that you have like sufficient disk space, you can always assume that you're able to consume the entire data set, write it to disk, do some operation, and then continue with the processing. In the streaming world, that's not possible. You want like low latency, so you cannot, and like data it will never stop. So your disk will just run full at some point. So if you're doing a batch join and you know that your data set is finite, you can be more efficient because you can load your entire data set into memory or on the disk, and then, for example, sort it on disk, and then do like a sort merge join of the data. You cannot do that in streaming because you cannot sort something that never finishes.
Yeah, you have to assume streams are infinite, so you can't possibly sort them. Yeah.
And what we are doing in SQL is that we're using windows if you need something to be finite. So if you want to chunk your data into daily batches in the stream processor, then you can do a daily window. So you collect data for an entire day, and only after a day you do some analysis based on this 1 day worth of data. And there's like many different types of windows. So you can do these what we call like tumbling window, where they're just discrete windows. Like for every hour there's a window if you do hourly windows, or you can do sliding windows where there is like every 10 minutes you're triggering a new window, and the windows are like 1 hour long. So they're like interleaved. Then you can do session windows that are dynamic, and you can do any kind of custom window based on your needs. So that's pretty flexible.
Okay, you can custom define them. I didn't know that.
Yes. So they're so the windowing API in Flink. So Flink has a built-in windowing operator that you can customize. So I think a typical customization is that you use a standard window, let's say a sliding window, but you trigger it more frequently. So theoretically, by default, you trigger the window when the hour is completed, if you're doing like an hourly window. But you could do something where you trigger the window every 10 minutes and then have like a final trigger after the full hour. And this way you can get results faster. So you can basically show your user, this is the data of the current hour, it's in progress. And then at some point you can tell your user, this is the finished hour. Like this is the final count or aggregation or whatever I'm doing of my data. And then there's like even more complexity to this. And this is about handling of time. Because when you're building a window, you can do windows based on count of your data. You can also say like, for every 1,000 elements, I want to do some analysis, but I don't think many users do that. Most of the users do windows based on time. And if you're doing that, then you have to cope with the nature of time and out of orderness. So imagine your data is coming from mobile phones and your users are sometimes in the underground or in an airplane or whatever they are on the countryside and they have spotty reception. So your events will not always, like when your user is liking stuff on Instagram, your likes will not arrive always when the user is clicking the button. The likes might arrive like 5 minutes later when the mobile phone has a reception again.
Yeah, and if you've got a 3-minute window, that's a problem.
Exactly. So, I mean, it depends what you're doing. So Flink has a lot of functionality for handling this exact use case. So Flink has a concept that is called event time. So you can tell the engine that in your data, some field, like one field, is the time at which the event has happened. So imagine your Instagram user that is currently on an airplane is doing likes. Whenever you click the like button, you assign the timestamp of the phone of the user to this event. Now the user is landing 2 hours later, and these events will arrive with a 2-hour delay. But the event time is the time when the event has happened, not the time when the data is arriving in Flink.
Yeah.
And then you can, if this window is still open, like still available, you can assign this to the right window. Or you have some custom logic that is handling late events.
So
like events that are arriving out of order.
So we're saying if you had a window that was a day long, then this is a non-issue. But if it's an hour long, you've already closed that window, shipped it off and said those are the results, right?
Yeah.
So how do you backfill that with the old data?
So that's something that Flink cannot solve. It gives you the means to solve it, but it doesn't solve it for you in a magic way. So this is something that you have to solve as the author of a Flink shop. So the window operator has multiple approaches. Let's say the one approach is that you have like a side output, like a special stream where late events are sent to. And then you run some custom code that is handling these late events. So imagine you're inserting these hourly aggregates of the number of likes, whatever, per country or so, into Snowflake. Then you could run a query in this special code that is updating the aggregate. So that the count from 2 hours ago is already closed, but you get this information that there is one last user, and you just update the count by 1 in Snowflake.
So your custom code is literally just running update statistics where time slot equals.
Yeah.
Yeah. Okay.
Because I mean the problem, the trade-off when working with out of order events or like late arrivals is always latency. So you don't want. So theoretically, you could keep your hourly windows, and this is actually what happens in Flink. So if you do hourly windows with event time in Flink, then Flink will keep multiple of these windows in its local state. And because it's basically collecting data for multiple hours at the same time. And only every now and then Flink decides that a window is done and it's closed, and then it's doing its computation on the window data and sends the result downstream.
Okay. So there comes a point where you say to the user, either you have to figure out a special way to handle this, or we can just drop it on the floor and say it's too late. Yeah. Okay.
Yes. So and this is all configurable by the user. So you can configure how long after a window has been closed you want to still keep it in case of late arrivals. And you can also define how Flink decides when a window is ready to be closed. Because that's another set of issues. Like if you're building hourly windows, how does Flink know when the hour is complete when it's working on event time? And for that, it's using a concept called watermarks, like low watermarks. And every source in Flink is emitting these watermark events into the stream. And these are special records that you cannot immediately see when you're implementing your data flow. But they allow you to track event time across your operators. So let's say in the Instagram like example with event time, at some point, the source that is produced, like that, where you're consuming these events from in Flink, like these like events from a Kafka topic, will decide how far the time has progressed. So it will basically say, based on the data that I've seen so far, I think that 2 p.m. has passed now.
Right. Yeah. So I've seen at least one event from 2 p.m., so it must be later than that.
Exactly. This is one approach. So you can say you basically just follow the highest time you've seen, and that's basically your virtual clock. What people typically do is that you add some lag to this. So you say, I saw an event for 2 p.m., but I'm actually assuming I'm just reducing like half an hour from this, subtracting half an hour from this, so that this event time is always lagging a bit behind. Like for half an hour, it's lagging behind, so that you can account for late arrivals. So if you know that you're willing and able to tolerate up to half an hour for late events, then you define your watermark so that it's always trailing for half an hour of the event time that you're tracking.
This is reminding me of meetups that say they're going to start at 7, but they have to start at 7:15 because no one shows up till 7.
Yes, exactly. Like, everybody who has ever hosted a party at home knows that you cannot start.
Yeah. You don't start on the dot. Yeah.
And so another approach that you can do here is, for example, that you build like a histogram of the distribution of how late events are arriving. And then you say, I want my watermarks to be covering 95% of the events, or 99% of the events, or whatever. And you're willing to tolerate like 1% loss, or you're willing to handle like 1% of late events using some custom logic.
Right. Yeah. Okay. So that leads naturally into if that's how you deal with user space being unexpected in its reliability, how do you deal with machine space being unreliable? What happens if I'm Netflix and my 250 gigabytes of state crash and die? What's going on internally there?
Yeah. So let's say the 250 gigabytes of state that Netflix is maintaining are actually 1 hour windows. So to just stick to the example.
Sure.
So you're so big because you're Netflix that your state is 250 gigabytes. And if any machine is failing, Flink will restore the state from the latest checkpoint. So Flink is periodically creating checkpoints that contain the state of all operators in your data flow graph. So let's say we have a Kafka source. The state in the Kafka source is the names of all the partitions and topics you're subscribed to, and the offset of the latest message that you've read. And then you have this window operator, and there it's all the data that is in the windows. So it's either some aggregate per hour, or it's all the data from the hour. And then there is a sink, let's say again, Kafka sink. This might also store some state if you're using exactly once Kafka sink. And if you're in, you configure a checkpointing interval, which means at this interval, Flink is making a backup of the state to some reliable storage outside of Flink. Typically these days, it's something like S3 or whatever your cloud provider is offering, like a cheap, durable storage where you're uploading your checkpoints to. So in our example, we could configure something like checkpoint every 5 minutes. So we will every 5 minutes upload the state of all the operators, in particular these 250 gigabytes of data from the window operator to S3. And yeah.
Okay. Does that mean it's snapshotting 250 gigabytes every 5 minutes? Or is it incremental? Is it cleverer than that?
Yeah, it's clever. So it supports it supports incremental checkpoints that only contain the diff from the last checkpoint.
Okay. And if that's so, what happens when that goes wrong? If I've got one of your 30 operator pipelines, maybe running across 60 machines, and one of them in the middle dies, I'm just trying to think how you coordinate all those different snapshots so that you get everything and don't reprocess something twice.
So you will reprocess data twice in case of a failure, but you won't count data twice. You won't have duplicates. This is the reason why Flink is considered, or we call it an exactly once stream processing framework. So it is exactly once with respect to state. It's not, let's say it's exactly once with respect to state, but it might still process data multiple times. So if a single operator in your Flink pipeline fails, it will reset the entire pipeline to the last successful checkpoint. There is an optimization, it's called local recovery in Flink, that the only on the failed machine you have to re-download the state. On the other machines, you can just reuse the files that are still on your local file system. So the checkpointing files are available on your local disk. So the recovery is not as painful as it sounds. Like you don't need to re-download 250 gigs. I don't know, you're downloading like 15 gigs or whatever of that failed machine. And then you can continue processing. So the trick how we achieve exactly one semantics is the way we create these checkpoints. So we are creating these checkpoints using a distributed snapshotting mechanism. So we are not just stupidly uploading the current whatever data we have on each operator, and this message, like when we are uploading, might be off, right? So you might have some messages that are in between and processed multiple times or whatever. We can guarantee that this checkpoint is consistent across the data. So how this works is that we are inserting a special event into the stream that is called the checkpoint barrier. So if you have the Kafka source, window operator, and sink, then it triggers on all the source instances via an RPC message. It just says, now do a checkpoint. So the source will upload its state to S3, and then it will, so the source will get this message. It will stop processing. It will upload its state. Then it will emit a special record downstream that says, here's the checkpoint, and then it will continue processing. So then in the output of the source, like you consider, like imagine a queue, and like there's regular events, then there is a checkpoint event, and then there's regular events again. And this checkpoint event will travel downstream to the join operator. Now the join operator will have multiple inputs, right? You have this as a distributed graph, and there's multiple sources, and the join operator will have to wait. So it will receive a checkpoint barrier on one of the input channels, and then it will stop accepting new data from this input channel, and it waits until it has received a checkpoint barrier from all the input channels. This is called the alignment phase of a checkpoint. And once it has received a barrier from all the inputs, it will create, again, a copy of the state of this operator. In this case, it will upload 250 gigabytes of state.
Okay.
And then the barrier is traveling through the system downstream to the next operator, which will repeat this until we reach the sink. And once we've backed up the state of the sink, the checkpoint is conceptually closed. Like, we have created a consistent copy of all our state at this particular point in time. And records are not allowed to overtake these checkpoint barriers. And because of that, if we have a failure now, we reset the Kafka sources to their offset that was there at the time of the checkpoint, and the contents of the window operator also to exactly the same point in time. So we will reset the state and the data, and this is in line. And this is how we can guarantee that we are not counting twice. So if your window operator is counting the number of records, we reset the counter to the right count at the time of this particular offset of the Kafka sources. So we will replay the data from Kafka, and the counter will go back a little bit, and then we will recount and continue processing after we recovered from the failure.
Right. So if I'm further down the stream in the operator pipeline, I'm going to get, hey, it's time to do checkpoint number 3, and I do checkpoint number 3, and I do checkpoint number 3, and I get some more rows. And then presumably there's another message that says, hey, I crashed, we're all going back to checkpoint 3, and I'm going to resend you rows from that point.
Yes.
Yeah. Okay.
Yeah.
Okay. That I can see how that makes the whole system consistent with respect to checkpoints.
And there is so these checkpoints are done asynchronously. So these 250 gigabytes of state in our window are, of course, our problem child that we need to give special treatment. Yeah. And what Flink is doing for the special treatment is that it will, when you're using, actually it's in the RocksDB on disk state backend and also in the memory-based state backend, it will create only a, let's say, snapshot of the data, like a view of the data at that point in time, and it will continue with the processing and upload the data to S3 in the background. So you can actually, the barrier can actually flow through the system quite quickly. It is only necessary for making sure that we are creating these state snapshots at the right point in time. And then in the background, there will be upload processes sending the files to S3. And only when the barrier has reached all the sinks, we need to wait that also all the asynchronous uploads that are happening are also finished. And only then the checkpoint is considered complete. And then we can use it for recovery. So if we are failing at any point in time, we just always go back to the last successfully completed checkpoint.
So at that point, you could nuke the cluster, reboot it, and expect to get back to where you were.
Exactly. Yes.
Okay. Cool.
And so this is the mechanism that Flink is using internally for recovery. But there's also user-managed checkpoints, and they are called save points. So you can also, as a user, say, you basically do like use the CLI or the REST API or whatever to trigger a save point. So you can also, as a user, say, hey, create me a copy of my state right now and write it to this directory. And then you can basically trigger a save point, like you're triggering a checkpoint out of band. So you're creating a special copy of your state and store it somewhere. And this allows you to go back in time. So if you create these save points like once a day and you realize that there was a bug in my code, then you can go back and say, okay, I'm replaying the save point from 3 days ago that fixes the bug. And then with event time, you will actually get exactly the same result. Even like it's like stream processing, it's supposed to be real time, but you can use it also for historical reprocessing or backfill.
Yeah, go back to that point in time. So presumably this gets used a lot when people are just before people are deploying on a Friday afternoon.
Yeah, for this, exactly for this, it's useful. It's also useful if you want to migrate your state from one cluster to another. So imagine, so I don't know, you just need to change your infrastructure for whatever reason. You can create a save point and restore the save point on an entirely different hardware. Or if you want to change the Flink version, like there's a new bug fix release, you create a save point, and then you restore with the fixed Flink version, and you can even use that to fix your job. So if you have a bug in your code and you want to fix it, you can restore with a different save point.
Oh, okay, so you do the whole thing along with a job. Is job the right terminology, actually?
Yes.
In Flink?
Yeah, we try to change the name to application, like stream application, but throughout the code and the documentation and in people's mind. So it's both job or application.
Right. Okay. So we're getting into what the developer experience is like for this, then maintaining it. But we've mostly been talking about as though this is a SQL-only world.
Yeah, it's not.
Tell me about the hierarchy of ways I can interact with Flink.
Mm-hmm. So there is two big APIs: the SQL API and the data stream Java, Scala, Kotlin, whatever JVM API. And the common ground, I would say, is the data stream API that that allows you to do high-level and low-level operations. So you can define your sources in Java. So you just define like a Kafka source and a Debezium source and a Pulsar source, and then you define like a window operator, and then you sync in Java, and you can like run your own code, of course, in like the maps and filters and so on. You can go one level down from that and use what we call the process function in Flink. And the process function allows you to access state directly. So you can say, I have a list state or a map state or a value state. So that's basically like a Java field in your code. But this field is backed by the state backend. So you can store terabytes of data in this field, even if your machine only has like 16 gigs of RAM or so. Because the data that you put into this list, for example, is actually written into RocksDB. And RocksDB means it's stored in a special file format on your local SSD, ideally. And if you're putting this into this state abstraction in the Java API, Flink will also checkpoint your state. So it will be recovered and it will be exactly once, like the mechanism that I've described. So the high-level window operator that is available in the data stream API is also using these state primitives. And you can access these state primitives in what we call the process function in Flink. And another benefit of this process function, like this low-level process function, is that you can access also time. So you can access the event time field of every record, like the current timestamp, and you can register timer callbacks. So you can say, wake me up in 30 minutes. And then I want to close my window or do some kind of whatever. So you can define callbacks. And then when the time has arrived for this callback, you get a special method call and you can do stuff like closing your window, for example. And this timer is either based on what we call processing time, like the wall clock real world time, or it's based on event time. So even if you're saying 30 minutes for this timer, it might, the system decides when to execute this timer.
Okay, so I could do something like, I'm thinking if I modeled an auction, I could accept bids in, but when I get a message saying the auction has now closed, then all future bids become irrelevant. The window closes at that point.
Mm-hmm.
Something like that.
And this like, let's say, custom windowing logic, you can implement this yourself with the process function. You have all the ingredients you need. You have access to the time of the bits, and you have the state, like list state, to store your bits in Flink state.
So is this what people generally do, that they write SQL until they hit something the SQL API doesn't support, and then they break out Java or Scala?
It depends. I mean, so let me finish a thought about the API. So DataStream is like the common API, process functions, the low-level API, and SQL is, of course, the high-level API. And you can use the SQL API within the Java program as well. So you can basically say you create your sources in Java, and then you just put a SQL string to do whatever you want, and then you continue in Java. Like you can also mix and match the different APIs, or you can go full SQL. Like you just use the SQL shell and you create your data sources and queries and whatever, everything in SQL. You don't have to touch Java at all. So now there's also extension points in SQL. Like you can do user-defined functions. So besides the built-in functions like concat and whatever, average, you can also do, you can define your own functions, and then you implement them in Java, or you can even use Java to delegate to Python or whatever language you want. So you can extend Flink SQL. So what I see as a pattern for companies building stream processing platforms is that they offer, let's say, business-specific user-defined functions as part of their streaming platform.
Oh, okay. So there's a department responsible for shipping a library of things everyone would find useful in SQL, that kind of thing. Yeah. Okay. Where do people tend to start with Flink? I mean, what's a typical way it gets introduced to a company?
So I think, it depends a bit on your skill set, like whether you're a Java developer or whether you're a SQL developer, and whether you're a lazy Java developer who knows that you can solve the problem in SQL. That's totally fine and makes a ton of sense. Like why? And honestly, SQL is highly optimized, of course, right? So there's like an optimizer that knows how to do an efficient data flow, and it uses optimized data types, and it uses code generation and all kinds of tricks to make this really efficient. So you would spend a lot of time expressing what you can express in like 15 minutes of trial and error with SQL. You would probably spend like a day or so in Java to make this really efficient. So it makes a ton of sense for many use cases to use SQL. And you can totally use Flink without knowing Java. You just define your data sources and things and write your queries, and you can do quite a lot with Flink SQL. So one way of getting started with Flink, if you just want to do SQL, is go to the Flink documentation and check out how to use the SQL client. Like you start Flink locally, like you just run a bash script that brings up a job manager and a task manager instance. And then you start your SQL client. It connects to the job manager, and then you can write your queries with it. If you're a Java developer, there's a different path that I would recommend, and that is you create a Java project, you add the Flink dependencies to your project, and then in your main method, you define like this execution environment of Flink, and trigger the execution there in your local IDE locally. So it will bring up the same components that you're running on a big 100 machines distributed cluster in your local machine. Okay. So you can really run exactly the same code that you're running on the big cluster also locally. It will bring up a job manager thread, and it will bring up a task manager thread basically in your machine.
Oh, okay.
And then
so it's not just running like a local client side part of Flink. It's running the whole of Flink.
As you wish. So you can, of course, use your developer machine to connect to a Flink cluster and submit your job to a big Flink cluster. But for development, it often, and if you're just getting started, you're not that sophisticated. You just go and press the run button in your IDE, and it will run everything for you. And you can even bring up the Flink web UI to investigate what's going on. You can configure checkpointing. You can configure the RocksDB state backend. Like all of that stuff also runs locally. And if you're a Java developer, that's my recommended way of getting started. It feels like developing against any other library. You just play with the code and add like log statements and put breakpoints for your debugger, and it's a pretty neat development experience. And you can even do like once you're done with the implementation of your Flink job, you basically create like a jar out of it, and then you upload it to your Flink cluster where it gets executed. And you can even do things like profiling on your local machine. So if you notice that there's some performance issue potentially on your cluster, you can run it locally again and attach a profiler to see where you're spending most your CPU cycles. And another benefit of this, it's again advanced use, but you can also use this local execution for testing, for integration tests, for example. So if you want to make sure that you're not breaking your production code, you can run a Flink mini cluster in your unit tests to make sure that you're not breaking anything.
Okay. And can I stub out my MySQL database for just a local static file source?
Yes, exactly. Yes. Okay. So in the Java code, basically there's a abstraction called the data stream, and a source is producing a data stream. So you can just put this behind a method, and then the method is producing or creating a stream of whatever you want. So you can just implement like a simple data generator in Java that is producing data that looks like the real data. And on production, you replace it with a Kafka source. For SQL, there is a data generator available as a source. So you can specify like basically the schema, and from the schema, the data generator deducts how to generate data for you.
Oh, sweet.
Yeah. So
that's quite cool.
Well, I mean, you basically define like an integer field, and then you say, I want to generate positive numbers or something.
Right.
Yeah.
Groovy. I have to ask for this. Is it any language I like as long as it's the JVM?
Yes, plus Python.
Oh, okay. There's a Python.
Yes, so there's a Python API as well for Flink that is fairly close to the SQL API or like SQL abstraction. So like between Flink SQL and the data stream API is something called the table API, and that's a Java way of saying SQL basically. So you can do like select, where, whatever in Java. And I think that the Python API is similar to that. And of course, you can run Python code. So you can also do a transformation with regular Python code, or an aggregation as regular Python code in your user-defined function.
Is it feature parity, or does it lag behind the Java version? Or has it diverged?
Yeah, I would say it has diverged, yes.
Okay.
So I think I'm not 100% sure. I have little experience with it, but it is fairly close to the SQL API, like the table API.
Okay. I need to go and check it out then. On which note, I just head to flink.org, right?
Flink.apache.org. So it's part of the Apache Software Foundation.
That saves me asking you what the licensing terms are.
Exactly.
Robert, thanks very much for taking me through all that, and I will see you again. Cheers.
Yeah, I really enjoyed the conversation. Thank you.
Robert, thanks again. I have to say, Robert's inspired me. Since we recorded that conversation, I've started using Flink in anger on some analytics stuff that I've been working on. Maybe at some point I'll show you. Maybe we'll do some coding videos for YouTube eventually. Something I'd like to do, time allowing. Another thing I'd like to do, and I think this time will allow, is a deep dive on more Apache projects. We've covered a few of them already on Developer Voices. Long term, I think we'd like to cover a lot more because there are lots of interesting ones. So if there's a particular Apache project you think I should be looking at, please let me know in the comments. On the topic of comments, if you've enjoyed this episode or found it useful, please take a moment to click like or share or rate or review, or whichever feedback-ish kind of buttons the platform you're listening to this on offers. Developer Voices is available on YouTube, Spotify, on Apple, all the usual podcasting places. They all have different buttons. Please go and find one. I am looking for your feedback on all of them. In fact, I might have some of that feedback data traveling through Flink, just between you and me, so why not give me some more datums to run through? On which note, I think it's time for me to leave you and for both of us to get back to the keyboard. I've been your host, Chris Jenkins. This has been Developer Voices with Robert Metzger. Thank you for listening.